So yeah, hi everyone. I'm going to be talking about a slightly improved approximation algorithm for metric TSP. And this is joint work with Anna Carlin and Shaina Vaskaran. And yeah, before I start the talk, I want to say, please ask questions if you have them. I think, this talk references some background that's common maybe in the area of approximation algorithms, but maybe not as well known outside of it. So I really welcome clarification questions. Okay, so in TSP, you're given as input a list of cities and their pairwise symmetric distances, which form a metric. So they obey the triangle inequality. And the goal is to find the minimum cost tour, which visits every city at least once. So if I live in Essen and I want to visit all the marked cities and then return home, then TSP will give me the shortest route which does so. And in particular, we're looking for any valid tour. So actually any connected Eulerian subgraph will work as a solution since such a graph exhibits an Eulerian tour. So if we think of our metric as a complete graph, sort of giving the distances between every vertex, then we're looking to find a minimum cost connected subgraph where every vertex has even degree. And for those of you who are curious why TSP is usually referred to as a min cost Hamiltonian cycle, it turns out that these are the same problem. You can always, using the triangle inequality, shortcut an Eulerian tour to obtain a Hamiltonian tour of no greater cost. But for the rest of this talk, I'll be looking just for a connected Eulerian subgraph. Unfortunately, TSP is NP hard. So to solve complex instances in a reasonable amount of time, we have to accept finding approximate solutions. And we say an algorithm has approximation ratio alpha if for every instance, the cost of its computed solution divided by the cost of the optimal solution is at most alpha. And the best approximation algorithm for this problem was from 1976 by Christofides and independently 1978 by Serdyakov, and has a ratio of 3/2, or in other words, it always produces a tour at most 50% longer than the optimal one. And it does so in polynomial time. And after a long line of work, we know it's NP hard to approximate better than 123 over 122. So we sort of have a long way to go in terms of understanding the approximability of this problem. These numbers are fairly far apart. Many of you may already be familiar with Christofides' algorithm, but I want to show it here as the algorithm we study is closely related. So here's an example graph we may wish to find a TSP tour on, or again, equivalently a cheap Eulerian subgraph. And in general, there are weights on the edges, but here feel free to think of every edge as having weight 1. And the algorithm first chooses a minimum spanning tree T, making the graph connected. However, since there are odd vertices, this doesn't correspond to a tour. Every vertex should have even degree, as whenever I enter a city, I have to leave it as well. So we add now the minimum cost matching on the odd degree vertices of the tree, which fixes our problem by making every vertex even. And now the green and the red edges together make an Eulerian tour. So now let's compute the cost of the tour. Clearly it's the sum of the cost of the tree and the cost of the matching. And since opt itself is a tree plus an edge, the cost of a minimum spanning tree is certainly less than the cost of opt. Now let's look at the matching. So I claim it's at most half the cost of opt. To see this, consider the odd vertices highlighted here in red along the optimal cycle. And now due to the triangle inequality, the restriction of the optimal cycle to the odd vertices costs at most opt. And now since there are always an even number of odd vertices, this subtour can be partitioned into 2 matchings. Here, one is in purple and one is in pink. And therefore, one of these must cost at most half of opt, and a minimum cost matching cannot exceed this cost. So that proves the second claim. And together, this gives us a 3/2 approximation. This is Christofides' algorithm. And since then, there's been a lot of amazing progress on approximating TSP. For example, in special cases such as planar TSP, meaning the distances are given by a planar graph. Here we have a 1 plus epsilon approximation for any epsilon. And also graphic TSP, where distances are given by an unweighted graph, we have a 1.4 approximation. However, the general case has remained at 1.5. And recently we made a tiny dent in this problem and improved upon Christofides' algorithm by some 10 to the negative 36. So I found this meme last year by Jakub Tarnowski, and you can see we actually get many, many more 9s than is written here. So I'm sad to say we're very far from making Boromir happy, but yeah, we'll keep working. So, okay. So here's an outline of the rest of the talk. Since this is a workshop on polynomials, I'll sort of ignore many of the more combinatorial details. But in order to convince you that the tools we develop in section 4 are actually useful for this problem, I first need to explain at least the rough outline of our approach. So I'll start with some background and by defining actually the algorithm we use. The first piece is pretty standard in the CS world. It's this linear programming relaxation for the problem. It asks for a fractional Hamiltonian cycle. So this means that every vertex should have fractional degree 2, and every cut should have fraction at least 2. So for example, this red cut has value 2, since the dotted edges are 1/2 here, making this a minimum cut of the support graph. This green cut, for example, has value 3, so it's satisfied, but it's not a tight constraint in the LP. And you can verify that this graph is a feasible solution since every cut has value at least 2. And this is known as the subtour elimination LP, or the Held-Karp relaxation. And note that even though I've written an exponential number of constraints, it can be solved in polynomial time via a separation oracle. It's easy to find a minimum cut in the support graph and just return it as a violated constraint if it's below 2. And we can kind of repeat this process. And note that this is actually a relaxation of the problem. The optimal integral solution is itself feasible for this program. Therefore, the optimal solution to this LP is a lower bound on the cost of an optimal integral TSP solution. So yeah, as is often the case, it's convenient to think of XE as the probability an edge E is in the tour. So this LP really gives us 2 benefits. First, we get a lower bound on the cost of opt. And secondly, we get a sense for which edges we might want to put in the tour. Okay, here's the second piece of background. A spanning tree distribution is lambda uniform if every edge has weight lambda E, and the probability of a spanning tree is proportional to the product of the lambda E's in its edge set. So for example, the graph on the left with lambdas 1/2, 1, and 1 would yield the following distribution over spanning trees. And it was proved in 2010 by Asadpour et al. That for any point X in the spanning tree polytope, we can find a lambda uniform spanning tree distribution in polynomial time that matches the marginals of X. And they do so using a max entropy convex program. So we can alternately think of these lambda uniform distributions as the distributions which maximize entropy subject to the constraint of matching the marginals of X. So kind of as an aside that many of you may know, this is actually an instance of a more general fact. Given any probability distribution mu and any point X in its Newton polytope, there's an external field lambda such that the distribution resulting from applying this external field matches the marginals of X. And if mu is strongly Rayleigh, then due to closure under external fields, this means that for any point X in mu's Newton polytope, there's another strongly Rayleigh distribution matching the marginals of X. And this is a sort of nice general fact. And just to say one more point on this slide, recall that uniformly random spanning tree distributions are SR, as they're a determinantal measure. And due to closure properties, applying the external field lambda preserves the SR property. So we know that these lambda uniform spanning tree distributions are themselves SR, which is a fact that we'll use. Okay, so now I can define the algorithm. And here we'll study an algorithm which is based on a work by my co-author Cheyenne, as well as Severi and Singh. And it's also very similar to Christofides' algorithm. Okay, so first we'll compute an LP solution X to the Held-Karp relaxation. And then given this X, we'll compute a marginal preserving lambda uniform spanning tree distribution mu on the support graph of X. And there is a small issue here, which is that the LP solution X is in the TSP polytope, not the spanning tree polytope. But it turns out this is easy. It's easy to convert a point in the TSP polytope to one in the spanning tree polytope, sort of without loss. So this is not an issue. And now we choose a spanning tree T from mu at random. And due to this marginal preserving property, in expectation, it costs at most opt. And finally, as in Christofides' algorithm, we just add the minimum cost matching M on the odd degree vertices of the tree. So our goal now is to use properties of our tree to show that the cost of the matching is less than half of opt in expectation. And since the tree costs at most opt, this would show that this is a randomized 1.5 minus epsilon approximation for TSP. I want to give some quick intuition on why it's important to find a lambda uniform distribution and not just any convex combination of trees. So here's a bad example, although there are many. So suppose we're looking at the unit metric, meaning every point has distance 1 from every other point. And suppose our LP solution is this complete graph on n vertices with 2 over n minus 1 on every edge. Then a valid marginal preserving distribution is to write the point as a convex combination of n stars. But now in every tree we sample, every vertex has odd degree, and therefore every matching costs n over 2. So this would not work. But it seems like I kind of picked an adversarial distribution. So the hope is that if we pick a distribution which is entropy maximizing, we might on average get something better. And yeah, personally I think lambda uniform trees also turn out to look sort of less like stars and more like trees we find in nature. And a little more formally, it turns out that when we sample from a lambda uniform distribution, we actually get trees that are so-called locally Hamiltonian, meaning that many vertices have degree 2 in the tree, and pairs of vertices have some chance of both being degree 2 and so on. And so this might already give you some hope that the algorithm works, since the optimal solution we're looking for is itself a Hamiltonian cycle, and now the tree already kind of looks like one. And we can prove this occurs by using the fact that lambda uniform distributions are SR, as I already mentioned. Okay, so I'll use this notation, delta of S sub t, to denote the number of edges in the tree in the cut delta of S. And a well-known fact about SR distributions is as follows, which I'll state for spanning trees, but it's true in general. So for any cut S, there exists some number of independent Bernoullis, B1 through Bm, such that the law of the size of the intersection of this cut with the tree is equal to the law of the sum of these Bernoullis. So in other words, for any k, the probability that the number of edges this cut shares with the tree is k is exactly given by the probabilities these Bernoullis sum to k. And this gives us a pretty nice constant. It says that for any cut with expectation close to 2, it's even with probability at least around 0.43. And since vertices have x of delta of S equal to 2, this says many of them are even, giving us this locally Hamiltonian property. In fact, many of them are degree 2, but recall that since the matching is only over odd vertices, really the important thing is that the vertices have even degree, not really that they just have degree 2. So I want to just pause on this fact for a moment, because although the proof is quite simple, it's a kind of bound we don't see very often. So these Bernoullis actually let us talk about the parity of a random variable and get quite a good bound on it. And it turns out it's quite important we get a good bound. We can't actually tolerate a number much below 0.43 in our proof. And if we only use concentration and say got a bound on the probability a vertex had exactly degree 2, that would not be enough for us. So yeah, long story short, many cuts are even. I'm very thankful for this Bernoulli fact. And if you don't want to listen to the whole talk, I would say you could stop here and just sort of take away this fact and the locally Hamiltonian property. And maybe you could convince a friend that this algorithm might work. Although obviously this is far from our proof. So given this intuition, I'll talk a little more formally about how we actually analyze the cost of the matching. Okay, so remember, we want to find the minimum cost matching on the odd degree vertices of the tree. And now to bound the cost, we'll use this matching linear program. So basically, instead of computing the expected cost of an integral matching, as this is a pretty hard thing to get a handle on, we want to instead show an upper bound on the expected cost of a fractional matching between the odd vertices of the tree. So here's the LP, and here's an example tree we might want to augment with a matching. And here the odd degree vertices are marked in red. So clearly you want to minimize the cost, and your variables are non-negative. So let's make sense of this second constraint. Basically, if you select a cut if you select a set whose cut has an odd number of edges in the tree, then by degree sum arguments, the number of odd vertices in that cut must be odd. So one of them must be matched outside the set, letting us add this constraint. This set, on the other hand, has no such constraint because these two vertices could be matched to one another. So this is the same thing as looking at sets with an odd number of odd vertices in the tree. And this LP has a very nice property. It has an integrality gap of 1. And this means that if we can construct a fractional matching of cost C, this means there must exist an integral matching of cost at most C. And since we just run a minimum cost matching, we'll definitely find a matching of cost at most C. So now the game is to find a cheap fractional solution to this LP, at least in expectation, and then our integral matching is guaranteed to find something at least that cheap. Any questions about the sort of overall strategy? Okay. And just to be clear about what I mean when I say even and odd, I'm going to use this as a kind of shorthand. We'll say a cut is even if its edges have even intersection with the tree and odd otherwise. And again, this corresponds to whether or not these cuts have constraints in the matching LP. It turns out it's very easy to get a matching of cost at most opt over 2, as in Christofides, but only by looking at this LP. So if we set YE is equal to XE over 2 for all edges, this is already feasible, since every cut has at least fraction 2 in the TSP LP, and therefore in this solution, every cut has at least fraction 1. So we actually just, using this solution, we satisfy every cut in the matching LP, not just these odd ones. And this costs half of the LP, of the TSP LP, and so we immediately recover this 3/2 approximation. However, as I said, this assignment simply makes every cut at least 1, so we're actually satisfying constraints that might not exist. So the hope now is maybe if a lot of cuts have an even intersection with the tree, and hence many constraints just disappear from this LP, then perhaps we can set YE to be strictly less than XE over 2 in expectation. For example, if some edges magically happen to be in no odd cuts, and therefore no constraints, we could set their YE values to be 0. So yeah, if we can gain some epsilon with respect to this initial feasible solution, then we would obtain a 3/2 minus epsilon approximation. Okay, so as I said, we can think of this XE over 2 solution as our initial point. And now we will perturb it a little bit by applying a slack vector that depends on the tree, such that we set YE to be XE over 2 plus this slack. And this slack may be positive or negative, but we'll want it to be negative in expectation. So think of us as starting at a feasible point, and then taking a small step in a direction which, in expectation, makes every slack negative. In other words, sending the expected value of every ye down. And so as long as S of E always keeps Y feasible, this implies that our matching costs less than half of opt. So now our goal is just to construct an S with these properties that's also feasible. And in order to help us maintain feasibility, our third criteria is that our slack vector will be very sort of subtle. We'll move variables by a tiny fraction eta at most, guaranteeing that each slack is at least negative eta over 4 times xe with probability 1. And it turns out that this third criteria lets us ignore all constraints in the matching LP that correspond to large cuts in X. In fact, the only constraints we're concerned with now, given this feasibility requirement, have X of delta of S less than 2 plus 2 eta. So if you take any cut that's larger, then due to condition 3, even if you set every slack in that cut to be minimal, this constraint would still be satisfied. So we never have to worry about large cuts now. So for the rest of the talk, we'll only be concerned with the small cuts, which I'll call the near minimum cuts. And I say near minimum because our LP ensures every cut is at least 2. So basically, we're looking at constraints that are very, very close to being tight. And eta here will be a very small constant. You may wish to think of it as being even 0. Okay. So yeah, since we generate negative slack from these sort of missing constraints in the matching LP, it's very crucial that many of these constraints corresponding to near minimum cuts are actually missing. So if all the constraints were there, the LP would just return the same value. So this approach only works for distributions that in expectation have many even near minimum cuts. So to go back to our example, we now care about these sort of red cuts, which are near minimum cuts of the LP, but we don't care about these green cuts, which have value much greater than 2. And note the vertices themselves are also minimum cuts, so we need to worry about these as well. So in remembering the star example, we might say that another reason this distribution failed is because it had no chance of making the near minimum cuts of the graph even. In particular, in this graph, the near minimum cuts are only the degree cuts. And in every single tree we sample, every near minimum cut is odd. However, as we already know, in our distribution, many near minimum cuts should be even. In fact, 0.43 of the vertices should be. And this would yield a matching of cost below 1 over 3. So this is not a bad example for our algorithm. And in general, if we have a graph where the only near minimum cuts are degree cuts, it turns out it's not hard to show that this algorithm works. So in this case, we can use a lemma which was proved in the paper from Avaiskaran, Sabarian, Singh in 2010, that any 2 near minimum cuts are even simultaneously with probability at least some constant p. And there is one important exception, hence the star, but I'm not going to go into that in this talk. But given this, the degree cut case is now easy. Pick any edge E. It's only in 2 near minimum cuts, its endpoints. Then with probability p, the tree that's picked has even intersection with both of its endpoints due to this lemma. And in other words, this is saying that with probability at least p, any edge E is in no odd near minimum cuts. And in this case, we can set its slack to be negative eta over 4 because all the constraints for small cuts are gone. And remember, we don't care about big cuts. And now each slack has negative expectation. It's 0 if an endpoint is odd, and negative eta over 4 times xe otherwise. So the degree cut case is good. However, this strategy, meaning setting slack to be negative if an edge is in no odd near minimum cuts and 0 otherwise, cannot work in general. Some edges may be in many, many near minimum cuts, and this could imply that their slacks are never set below 0. And these edges in many near minimum cuts may sort of be the expensive ones. However, hope is not lost. Maybe if we can obtain a laminar family of near minimum cuts, where at each level we just have degree cuts, then maybe we can apply this logic at every level and somehow just deal with edges that appear in many levels. And this is exactly what we do. We show that there's essentially a reduction to the case in which the near minimum cuts form a laminar family. But I won't talk about this since it's not at all related to geometry of polynomials. But given this hierarchy, we can now exploit properties of strongly Rayleigh distributions to construct a slack vector that works on any laminar family of cuts. So I'll briefly describe this inductive approach before introducing our two tools. So here's a valid hierarchy we might obtain. And now an edge's height is just defined by the level of the hierarchy that contains both of its endpoints. So here the pink edges are higher than the red and the blue edges, and the purple edges are higher than the pink edges, and so on. And at a high level, what we'll now do is as follows. We'll initialize all slack at 0, and then we'll define local conditions for decreasing slack. We'll decrease an edge's slack when it is in no odd cuts on its top level. And this matches the intuition that we perform induction over the degree cut case. So for example, the top level of these pink edges is this pink cut. And now when we view this pink cut in isolation as a graph with only degree cuts, viewing these green sets as contracted points. And for these pink edges, these green cuts are their top two cuts, terminology I'll be using for this section. And now the pink edge's local condition is the same as in the degree cut case. We reduce their slack when both of these green cuts are even. This reduction may unfortunately need to trigger increases in other edges' slack lower down in the hierarchy. We only did this sort of very local conditioning. But basically trading off between these local decreases and these more global increases is basically the essence of our approach. So more formally, we decrease slack for this local reason if an edge's top two cuts in the hierarchy are even. So for example, look at our pink edge E. L2 and R2 are its top two cuts in the hierarchy. So if the black edges represent the sampled tree, here we would not reduce the slack of the pink edge, as both L2 and R2 are odd. L2 has 3 edges and R2 has 1 edge. However, if we sampled this tree instead, then both cuts are even. So now we can reduce SE by its maximum possible reduction. So this is the decrease event. However, we only condition on L2 and R2 being even. We only looked sort of very locally around us. And we don't know whether L1 and R1 are even or not. And if they're odd, these constraints are actually violated in the matching LP, since they were nearly tight to begin with, and we decrease the value of an involved variable. So what we'll do is actually increase the slack of other edges to make up for this issue, for this decrease of E. So in this case, R1 is odd, so we must increase some f of I to make up for E's reduction. L1 is even, so no increase is needed. And what we'll end up doing is performing a matching such that whenever E is reduced and a cut lower in the hierarchy containing E is odd, then an edge group of similar fractional value will increase. So here, say F3 is matched to E, and they have a similar fractional value. Then we guarantee that whenever E is decreased and R1 is odd, we increase the slack of F to fix this constraint. Something important to keep in mind is that if an edge is reduced, it definitely does not have to increase its slack for any edge going higher. And this is because it only has to potentially increase slack for its top two cuts. But the decrease event implies that both of these cuts are actually even. So the increase and the decrease events are disjoint, and it only remains to show that the expected decrease of an edge is greater than its expected increase. And I think of the increase event as sort of a global response to these local decrease events. And this is because the decrease event may trigger sort of thousands of increase events. So in this example, you can think of E as being in many, many cuts. And when it's decreased, maybe all of these red cuts are odd, even though E's top cut is even. So this decrease on E may trigger the increase of many, many other edges. Okay, so I won't go into too much more detail than that, either fortunately or unfortunately, depending on how bored you are. But to summarize, we first want to find good local conditions under which we decrease slack. And I mentioned the condition that we reduce when an edge's top two cuts are even, but it turns out we often need to go beyond that and provide stronger guarantees. And then we want to bound the probability that edges need to increase to compensate for reductions on other edges going higher. And this involves proving bounds on the parity of cuts conditioned on the slack of other edges being reduced. So basically, we want to understand the probability that one of these cuts sort of lower down in the hierarchy is even, conditioned on E being reduced. And to get a handle on these 2 points, we prove 2 lemmas about strongly Rayleigh distributions that may be of independent interest. Okay, so we first proved that for any k disjoint sets, each with expectation close to 1, there's a constant probability that each set has intersection 1 with the tree. So in this example, there's a constant probability that each color has exactly 1 edge. More formally, we prove a generalization of a lemma from a paper by Gervitz from 2006. We show that if you have k disjoint sets and their expectation is close to the all ones vector, then the probability that every set has intersection 1 with the tree is a function of only k and epsilon. I'm using t and tree here, but again, this holds for general SR distributions. And I call this a generalization as this was previously known for k subsets that each had expectation exactly 1, and now we allow some deviation. And recently, as we saw in Jonathan's talk on Wednesday, Gervitz and Leek proved a related theorem which has a much better dependence on k and allows deviation up to 2, but only holds for homogeneous distributions. So for now, these are sort of incomparable, but maybe they'll be able to remove this homogeneous criteria. And our lemma is actually stated in terms of probabilities. So here's its alternate form. And it can actually be generalized to sets of any size, not just size 1, but I'm stating it for sort of sets of expectation, each close to 1. And having a probability here is useful since in some cases, we don't have a bound on the expectation, but we can still prove something about these probabilities. And just to quickly highlight the differences between these 2 lemmas, although you should see Jonathan's talk for a lot more detail. Basically, our lemma works for non-homogeneous distributions and again uses probabilities instead of expectations. But the bound is much worse. We get this doubly exponential thing. And I also want to mention that their proof seems to use sort of the right tools, going more through the geometry of polynomials. So I think there's some hope it can be extended to get epsilon to the k in our regime, whereas our proof technique seems maybe more unlikely to get this bound. And I want to point out that requiring these AIs to be disjoint is a huge issue for us. In fact, they're never disjoint in our applications, as we're always talking about a collection of cuts that all share a particular edge that we want to get a local condition for. So basically, we always end up doing some strange kind of manual work where we first do some conditioning to make these AI disjoint, and then we apply this theorem. And when we do the conditioning, we have to kind of bound the changes on the AIs. So this is not ideal. And this suggests the question, is there a good sort of characterization of the necessary disjointness conditions on these AI? So it seems we sort of understand disjoint sets now, but we don't have precise tools for sets that overlap. I think this is a good open question. So why is this useful? Basically, instead of only proving that the top 2 cuts of an edge are even with constant probability, we now want to go farther and prove stronger local conditions, such as the top 4 cuts being even. Say for this pink edge, we want L1, L2, R2, and R1 to all be even simultaneously. And this is useful because it just means that less increase needs to occur. Previously, we had to increase on the R1 cut for the pink edge whenever it was reduced and R1 was odd, but now that never happens. Whenever the pink edge is reduced, we're guaranteed that R1 is even. And in some sense, this lemma lets us talk about any k cuts simultaneously. However, due to the disjointness issue, it's difficult to characterize exactly when we can get all k cuts to be even with constant probability. For instance, there are even some counterexamples for k equals 2. So actually obtaining these local conditions can be a bit tricky. Okay, and second, we prove a related fact for 2 disjoint sets A and B of expectation again close to 1. We show that there's an event of constant measure, which approximately preserves the marginals of all the edges in A and B, and guarantees that when this event occurs, A and B each have intersection 1 with the tree. So for example, conditioned on this event, we know A and B are both 1, and we know that the marginals of this pink edge, so the probability E is in T condition on this event, is still approximately 1/2. And here it is written formally, for any 2 disjoint sets A and B with expectation close to 1, there's a marginal preserving event, E of AB, of constant measure, in which each of A and B have intersection 1 with the tree. And again, these total variation distances are preserved up to factor epsilon. And this epsilon we can get here depends on the distance of A and B from 1. Okay, and so now how do we use this? Suppose that we can align an edge's local condition with this lemma. And it turns out that if an edge's top 2 cuts look like this picture, where they both share fraction 1, then we can do exactly that. Here, E is even exactly when the top 2 cuts, here E is even in its top 2 cuts, exactly when A and B have intersection 1 with the tree. And using this, we can obtain more control over this more sort of global impact of reducing an edge's slack. And this gives us a lot of control. So while under some local conditions, the distribution may change quite a bit, whenever we can apply this second tool to get an edge's decrease event, we know that basically the distribution is unchanged. So to go back to our picture, basically with this lemma, conditioned on the reduction of E's slack, any cut lower down in the hierarchy still has a 0.43 chance of being even, because we've preserved marginals, and actually it turns out that we preserve the strongly Rayleigh property for every cut below this edge. Whereas without this lemma, it can be difficult to get any bound on this probability. It can be difficult to even say that the probability this cut S is greater than, say, 0.01. And one issue we have is that this lemma cannot be used in every instance. And in those cases, we have to more manually sort of ensure that the cuts lower in the hierarchy have some chance of being even. So another open question is to characterize exactly which situations where we can approximately preserve marginals. And the marginal preservation may not need to even be that close. In fact, for us, even preserving marginals up to, say, a constant multiplicative factor could be kind of interesting. So I think this is also a good tool to think about generalizing. So yeah, with these ideas and some elbow grease, we get a small improvement for TSP. So here's some open directions. So first, we would like to improve probabilistic tool number 1 in a few ways. The most natural question is, can we get this tight bound of epsilon to the k? And yeah, maybe Hurwitz and Leek can do this. And the second is whether it's possible to characterize the necessary disjointness condition for this lemma to hold. as I said, we mostly got around this problem by first doing some conditioning and then applying the lemma on the resulting disjoint sets. But we think there should be some clean description of when it works and when it doesn't work. And finally, we ask whether it can be generalized to log concave distributions. And secondly, we ask if probabilistic tool number 2 can be generalized to any number of sets. So I stated it for 2 sets, but we think maybe it works for any number of disjoint sets. And then sort of what trade-off can be obtained between the distance of these sets from the all ones vector and the total variation distance, or maybe some other measure of the marginals in the resulting event. And finally, we ask whether there's some totally new way of analyzing this algorithm. So empirically, the algorithm seems to do quite well, and we know no example where it does worse than 4/3. However, our analysis seems doomed to only beat 3/2 by a small constant. So our main question is whether there's a new approach which can get something significantly better than 3/2, or maybe an example where the algorithm doesn't do so well. Yeah, so with that, thanks a lot for listening and for having me. Here's a picture of some TSP soup by Bosch. So I'd be happy to take any questions.
Thanks a lot, Nathan. It's a really great talk. Any questions?
We cannot hear you, Milena.
I was not speaking.
Oh, sorry, I thought you were speaking. There was a...
So in this area, there's some conjecture about what the optimal approximation ratio should be, right? So is there any prospect of these techniques getting close to that?
Yeah, so the conjectured bound is 4/3. I think you would need some totally new ideas. Yeah. Probably we can't do much better than like 1.49 or something. Yeah.
But could you comment on where this, like what the weakest part of the argument is in terms of the constant? Like,
yeah, so there's basically 2. The first is that we only look at these cuts between 2 and 2 plus eta. And the bound you get cannot be better than 3/2 minus eta. So immediately you'd want to look at cuts that are much, much bigger than just near minimum cuts. So that's one issue. And then the second issue is that even now, given this, these very small cuts, we still don't have a good argument to get anything close to eta. So we get 3/2 minus like 10 to the negative 20 times eta or something like this. So you'd have to really improve both of those pieces by quite a lot. But yeah.
And it's very unforgiving. You'd have to get like 1 times eta or something.
Yeah, exactly.
Okay,
yeah.
fine.
So it's or maybe like 1/2. But yeah, it's like pretty. But I think the really fundamental thing is just how big are these cuts you're looking at. I think it'd be interesting to look at maybe cuts as big as like 3 and see what happens. But yeah.
So this laminar family stuff doesn't work does that break down when you look at bigger cuts?
I think it works up to like some sort of reasonable sounding eta, but nothing probably bigger than like 1/100 or something. But the eta we choose also has some implications for the other argument, and in the other argument, we need eta to be very, very, very small. So yeah, there's just sort of a lot of constraints going on here. Yeah. But one direction we're kind of interested in is sort of taking the dependence on eta out of the second argument in some way. And I think that could be, couldn't get 4/3, but maybe we could make Boromir happy. You could get like 1.499999 or something. Yeah. So we'll see.
I think one constraint is that eta must be less than the probability, the the probability that multiple cuts are even at the same time, which is some sort of this doubly exponential that we have. So eta must be less than that. The approximation factor is less than the product of the two.
Right.
So that's the simplest.
So even if you improved it to exponential, like in this Leak and Grover's thing, that would still, yeah.
It would still, yeah, it helps, but not so much.
Okay, well, thanks again. So the next talk will be at 10.